All right, so today we're gonna see vectorized code and revisit indexing that I showed you in the first lecture. And I'm gonna show you how to logically index matrices. Last week we covered for loops. Even though MATLAB has for loops, if you can, try to avoid them. If you can do, if you can write a code without a for loop, you should do so. So for instance, in this block of code, we are multiplying 3 with each element of the for loop. Okay, so I have a for loop that goes over each row and then each column and multiplies the element indexed by that row number and column number with 3. How can I rewrite this code in MATLAB to achieve the same thing? In one line. So I want to multiply each element of the matrix with 3, right? I would just say m equals m times 3. That will multiply 3 with each element. The answer is down there. Logical vectors are vectors that have the data type true or false. They have logical data type. So each element of a logical vector will have a value true or false. You can construct logical vectors using relational operators such as greater than sign. For instance, in this example, I have a vector that contains these numbers, and then I'm checking whether each number is greater than 4. So you can think of this as a mathematical operation where you compare each element of vec with the number 4. So you will get as a result 1 greater than 4, 5 greater than 4, 8 greater than 4, 9 greater than 4, 2 greater than 4, and 7 greater than 4. And then that will reduce to 0. Let me actually rewrite it as true or false. So this vector will be equal to false. What's the next one? True. Next one. False. Next one. True. And then false. And true. If you try this in MATLAB, instead of trues and falses, MATLAB will display zeros and ones. Okay, so it will be displayed as 0, 1, 0, 1, 0, 1. Even though MATLAB displays them as zeros and ones, it's not a numerical data type. Okay, and if you look at the workspace, you can also type the whos function that will show you the contents of the workspace. The isG vector is a logical array. Okay, even though MATLAB displays zeros and ones, the type of the data contained in it is logical. So they are trues and falses. You can take a logical value, a logical vector, and perform mathematical operations on it. But as soon as you do that, then they are converted to zeros and ones, and they become numerical data type. So when you add plus 5 to this logical vector, the result will be a numerical vector. So you just add 5 to this vector, you get 5, 6, 5, 6, 5, 6, and the result, which is stored in the double res variable, is a double array, which is a numerical data type. Okay. If you have a logical vector or a logical matrix, you can use it to index a vector or a matrix of the same size. So again, our example, this is the vector that we are dealing with, and we construct a logical vector where if the element of vector is greater than 4, we get a true, otherwise we get a false. Okay, so let's rewrite it. So we have a 0, 1, 1, 1, 0, 1. And to denote that it's a logical vector, I'm just going to make this symbol. I'm just going to put a line here to make sure that I know that it's a logical vector. Okay. MATLAB doesn't have it, it's just for visual purposes that I'm using. Now, if you use this logical vector is G to index the vector vec, what you are essentially doing is you are picking from vec elements that have true in your index. So I'm not picking the first element, which has a 0 in my logical vector. I am picking out the second element, 5. I'm picking up the third one, 8. I'm picking out the fourth one, 9. I'm not picking this one, and I'm picking the last one, 7. Okay. So this is equivalent to saying vec get me the second one, third one, fourth one, and sixth one. Okay? So if you have a logical vector that has the same size as the original vector, you are picking elements that have a true in your logical vector. Alright? And in addition to reading out those values, you can also change the elements that you are referring to. In this case, I am changing the values of vec referenced by isG, logical vector. And the same vector is showing up on the right-hand side, and I'm adding 1 to it. So what that will do is it'll take this vector, 5, 8, 9, 7, add 1 to it, and I get 6, 9, 10, 8. And then it will take this vector as a result of the right-hand side of the equation sign and store it in the boxes referred to on the left-hand side. And those are, again, the second, third, fourth, and sixth entries in the vector. So as a result, I am replacing the second element, which becomes 6, the third element, which becomes 9, the fourth one becomes 10, the fifth one is not referenced, is not changed, so it remains as 2, and the last one becomes 8. Okay? Is that clear? Are you guys with me so far? Okay. Now let's use this concept to take this vector A and create another matrix B that contains only the even elements of A. So can you guys tell me an expression that will accomplish that? So I want to take the even elements of A and put it into the new variable B. Any ideas? All right, let me repeat this in MATLAB. Say that again? Yes, so I can use modulus of 2, and then that will tell me whether the number has a remainder 1 or 0 when you divide it by 2. And then I need more steps after that. Where's my MATLAB? Here we go. Okay, so the variable A contains 521,796, and I want to extract from this vector only the even elements. So how do I check whether an element of this is even? I can divide it by 2 and get the remainder. That's accomplished by the modulus operator. Okay, so it'll give me a true whenever, sorry, a 1 whenever the remainder is 1 and a 0 whenever the remainder is 0. And you can look at the workspace and see that the answer variable is a numerical data type. Okay, so even though you see zeros and ones, it's not true and false. It is numerical ones and zeros. And then I would take this and compare it with 0. Alright, so they'll give me a true whenever the remainder is 0. Sorry, they'll give me a true, which is a 1, whenever the remainder is 0, and a false, which is a 0, whenever the remainder is not 0. Okay? So by using this expression, I'm able to extract contents of A that are even. And I can store that in a variable I. Equals 0. Okay? Now if you look at the workspace, the variable I is a logical vector. So even though MATLAB shows zeros and ones, these are stored as falses and trues. Next, I can use this vector to index A. So I'm picking out from A the entries that have a true in this logical vector I. Right? So you overlay the variable I on top of A and pick out the values of A that has a true in the vector I. And that gives you 2 and 6. Let me show you A again and I. And then the last expression was AI. Alright? So you would go through I, and whenever you have a true, you would go to the corresponding element in A and copy it to your output. So you have a 2 and you have a 6. And the question was asking us to store this in a variable B. And this is how you would do it. Instead of saving the result in a temporary variable I, you can do it all in one line by writing the expression that you used to find I, and it'll give you the same result. Okay? So initially we stored this in a temporary variable I, but you don't really have to do it if you don't like using temporary variables. Any questions? Okay. Now the next part asks us to add 1 to odd elements of A. Now to figure out the even elements of A, I was using mod A 2 equals 0, but I want the negation of that. So I can negate this expression, which will give me 1 whenever I have a 0, and it will give me a 0 whenever I have a 1. Alright? So that will give me a logical vector where I have a 1 for even elements of A. Another way of doing it would be to test whether mod A2 is equal 1. That'll give you the same result, because you only have 2 options when you are dividing by 2. The remainder will either be 0 or 1. Okay? And then I would store this in a temporary variable I. Now I have my logical vector, which I can use as a map that I can overlay on top of my original vector A. And it'll give me the odd elements of A. And then I can add 1 to it and store it back in those elements of A. Okay? So I should not just say A equals A sub I plus 1. That would get rid of the contents of A and replace it with this new vector. I only want to change the odd elements of A while keeping the even elements of A as they were before. So I need to only refer to the odd elements of A on the left-hand side using the same logical vector I. So that will change the odd elements of A, and they will all become even, because when you add 1 to an odd number, you get an even number. All right? So this was the original values. And then I constructed a vector that contains logical true for odd elements. And then I used it to update the odd elements of A. So 5 became 6, 1 became 2, 7 became 8, and 9 became 10. And the even elements are not changed, because I did not reference them on the left-hand side of this equation. All right? Are you guys still with me? Okay. All right, so maybe you should try this on your laptops. I'll give you 1 minute. You just need to tweak around the expressions that I just wrote on the screen. And it's asking you to remove all elements of A that are divisible by 3. So as a result, let's assume that we start over again from this original A. And as a result, you want to get 5, 2, 1, 7, and then 9 and 6 are removed because they are divisible by 3. Right? When you are done, raise your hand, and then I'll show you the answer. Now I can use a similar expression to test whether the elements of A are divisible by 3 by just replacing with this 2 with 3. So let me reset A to be that, and mod of A divided by 3, and I'm checking whether the remainder is 0, and that will give me a true only when the elements of A are divisible by 3. So only the last 2 are divisible. So I get a logical vector I that contains falses and trues. The first 4 of them are false, and the last 2 are true. And I can use this logical vector I to index A. So AI will pick only the values of A that have a true in this AI, and those are 9 and 6. Okay, and I can update those. Oh, sorry, the question is asking us to remove it. I can do any operation on them. I can set them to 0. So that will set the values indexed by I with 0, or I can remove them, and they are removed from the vector A. The last question is asking us to repeat the step when A is a 2 by 3 matrix. So nothing will change. All of the expressions will be the same, because the way that mod operator works and the logical indexing works, you don't really need to change anything, except there are some differences in the removal question. So let's repeat the first one. Now A is a 2 by 3 matrix. We want to create another matrix B that contains only the even elements of A, so I will construct a logical vector I that tells me whether an element is divisible by 2, and then I will set B to be AI. Okay. Now the next problem is asking us to add 1 to the even to odd elements of A, so I am constructing a logical vector I that contains a true wherever A is odd, and then I am adding 1 to them. Okay. Now when you remove an element from a matrix using logical indexing, you don't get a matrix. You get a vector. So I'm constructing this logical vector that contains a true whenever the element of A is divisible by 3. And then I'm removing from A those elements. Okay, so I get, as a result, I get a vector instead of a matrix. The reason being, if you remove arbitrary elements of a matrix, let's say we remove this guy and this guy, there's no way for MATLAB to know, well, if it just removes those, it'll give you holes in the matrix. Okay? That's why MATLAB will just linearize this vector and perform removal operation on the linearized vector. Okay? So AI equals empty vector is equivalent to saying A equals A colon, linearize it, and then AI equals empty vector. Actually, you also need to linearize your logical vector. All right? So removing elements, individual elements from a matrix results in a vector instead of any matrix. Now, I already told you that when you see zeros and ones in MATLAB display, those may not be numerical. And you cannot use a logical, you cannot use a numerical zeros and ones as your index. And MATLAB will give you an error saying that the indices must be real positive integers or logicals. So in this example, what I'm doing, I'm trying to access elements of A defined by this logical vector. But the problem is that when you just type zeros and ones, it's not a logical vector, it's a numerical vector. So MATLAB will try to access the first element of A and then try to access the 0th element of A, but there's no 0th element in A, so that's why you get an error. All right? If you just say A 1 1 1, you would not get that error because it will just pick the first one again, the first one again. And the result of this will be 5 5 5 for this example. So when you want to use a logical index using zeros and ones, you have to first convert it to a logical data type. And to accomplish that, you can either enclose it with the logical function that will take a vector and return a vector with the same size where all zeros are replaced with false and anything that's not zero is replaced with true. Or you can write out the entire logical vector yourself by typing true whatever you want at 1 or a true, and typing false whatever you want a false. Okay? Now you can take a logical vector, or in fact any numerical matrix would also work, and apply the find function. And find function will return the indices of non-zero elements of X. All right? So let's figure out what this first one will do. If you give it this vector, it'll go through the vector and see which ones are non-zero. So the 3 is non-zero, 2 is non-zero, 5 is non-zero. And then it'll give you the indices of those. So 1, 3, 4. The first element, the third element, and the fourth element. That's the result you're going to get when you call the find function on this vector. The same thing applies when you give it a logical vector. Now falses are zeros. Non-zero elements are trues. So the result will be the second element is true, and the fourth element is true. So that's the result you're going to get. All right? Let's do the last one. Vector contains these values, and you construct a logical vector that will contain true whenever the value is greater than 5. So let's write the result of that. You get a false. This is going to be a logical vector. False, false, true, true, false, true. And then you take that and give it to the find function, and the find function will find the non-zero elements and return their indices, the third one, fourth one, and the sixth one. Okay? Now, if you have a logical vector I, you can either use that directly to index your matrix or your vector. You can also apply the find function and get a numerical vector and use that as the index. And those two ways of indexing your matrix M are equivalent. Okay? All right. There are a number of convenience functions that let you operate on logical vectors or logical matrices. Here, I have a numerical vector, vec1, that contains 1, 3, 1, 1, 2. The any function will give me a true if at least one of the elements is non-zero. Okay? So it'll go through the vector. If it can find at least one non-zero element, the result will be true. So if you write a for loop, you would see that the first element is not 0, and then you don't really need to look at the rest. You can just return true. So the result of this will be true. All function goes through the vector and returns true only if all of the elements are true. Okay? So only if all of the elements are non-zero. So if you write a for loop, you have to look at the entire vector, and if they are all true, you would return true. Another way of thinking about it is that if at least one of them is 0, you would return 0. Make sense? All right. So now I have another vector 1, 1, 0, 1. What's any vector? Applying any function to this vector 2. If any of the values is true, then the result is true. So if you write a for loop, the first one is true, you don't even need to look at the rest. The result is true. Okay. What's the result of the second one? Okay, false. So are all of them true? The result is no. Okay? Alright, when we discussed conditions in the selection chapter, in the selection lecture, we used double AND or double OR to construct an expression whether both sides were true or both sides were false. Well, using the AND Boolean operation or Boolean operation. When you want to apply these two vectors, you cannot really use double AND signs. You have to use a single AND. Okay? So remember when we were doing matrix operations, if you say x times y, this could be a matrix multiplication. If you want to ensure that elements of x are individually multiplied with elements of y, then you had to do dot multiply, right? Similarly, if you have an x vector and a y vector, instead of saying and, you need to use and if you want individual element-wise AND operation. Okay? Now, if let's call A and B are scalar, then the result of A and Y is equal to the result of A and N. Sorry, this has to be B. So when A and B are scalar, using a single AND or a double AND give you the same result. Alright? So with this information, can you guys tell me what the result of B1 and B2 will be? What's the first element? Is it going to be 0 or 1? 0. So whenever you see an AND, you are multiplying the numbers, okay? So 3 times 0 is 0. Next one. Next one. 1, 0. Okay, good. When I'm ORing it, I'm adding up the numbers. So what's the result? 1, 0. Should I not be asking you guys? Should I not be asking you? Are you offended that it's too easy that I'm asking? Okay. You guys are not replying, so I don't know what's going on. Okay, is it going to be 1? Good. So you have to be careful with my analogy that you are adding them. Let's give an example. Minus 3, 3, 5, 0. Let's call this X. Let's call this Y. So what's the result of X and Y? 1, 0, right? So before you multiply them, convert them to 1s and 0s and then multiply them, okay? And then likewise, when you are ORing them, don't just add them. First convert them to 0s and 1s. So both of these will be converted to 1s because they are non-zero. And the result will be 1, 1. Alright? Yeah. So you are first converting them to 0s and 1s, so you get 1 and 0, and then you say 1 plus 0, which is 1, and then you get a 1. Alright? And then this part you added, you converted minus 3 to 1, and you converted 3 to 1. You add them up to, it's a true, so you get a 1. Okay. Alright. Any questions? Alright, since we now have 2 additional operators, we need to know where they go in the order of operations with the other operators that we had. So let's review them. We have the parenthesis has the highest precedence, and then the transpose and power, the unary operators. And then we have the arithmetic operations, with multiplication coming before addition. Then we have the colon operator. After that, we have the relational operators, and the new operators that we just discussed are element-wise logical operators, and the original logical operators that work on only scalars come after those. Okay? So if you see a complex expression, these are the order of operators that you need to consider. And you would apply starting from left to right and following the precedence rules. Alright. So when you want to operate on elements of a matrix that satisfy a condition, you would first construct a logical vector or an index. It can either be a logical vector that has the same size as your matrix, or it can be an index that contains numerical entries that correspond to that logical vector. And then you would use that to index your matrix and perform operations only on those elements that you are indexing. Now let's use that concept on this problem. We have a matrix A, and the magic square is a convenient way of generating an example matrix, and it has the property that the sum of the rows and the columns are the same. And in this case it's 1379. It's 34. Okay. So if you construct a magic square matrix that has 4 rows and 4 columns, the sum of each row is 34 and the sum of each column is 34. All right. I use it frequently to construct an example matrix. I've also constructed example matrices using rand in the past, or rand I. So 10, 4, 4. That'll give me a random matrix that contains values between 1 and 10. Alright, so given this magic matrix, I want to replace with 0 all elements of A that are odd and whose logarithm is greater than 2. Okay. So you can do this with for loop. And using for loop, I would do for I equals 1 to the number of elements in A. And then I would check if that element is odd. So modulus AI 2 equal 1. And the logarithm of this number, log AI, is greater than 2. Then I will replace that element with 0. Okay? So this is what I want to do using logical indexing. Now you have you are iterating over your vector or a matrix, and you are constructing a condition. You have a condition that will be true only when it's odd and its log is greater than 2. And you are only applying equals to 0 on those elements. So if I had an index I where it has a value 1 only when this condition is met, then I can write the same function, the same functionality by saying AI equals 0. Okay. So the problem now is, how do we construct this index I? Now both the modulus operator and the logarithm operator work on matrices also. So instead of saying modulus of AI comma 2, I would say modulus of A. And it will give me the remainder of A divided by 2. And I can just say equals 1. That'll give me a matrix wherever the element of A is odd. And then the next part is, again, I would say logarithm of A greater than 2. That'll give me a true wherever the logarithm of A is greater than 2. And then I would AND these together, but now instead of using double AND, I need to use element-wise AND, because both sides can be a vector or a matrix. Alright? So let's write this in MATLAB. A equals magic 4. Modulus of A divided by 2 equal 1. They'll give me a matrix that has the same size as A, and it will contain 1s wherever I have an odd number in A. Okay, so let me store that in the matrix X. Now the next part is taking the logarithm. If you take the logarithm of A, it's taking the logarithm of each number in A. And I can compare that with, what was the number? With 2. And that'll give me a true wherever the logarithm is greater than 2. All right? Let's store that in a variable named y. So now I have the variable x, I have the variable y, and I can AND them together. And when I AND them, I will get a new matrix that has the same size, and it will contain a 1 only when the corresponding elements in x and y are 1s. So I'm doing element-wise ANDing, element-wise multiplication, if you will. All right? So that's the result. So this is going to be my index. The elements that have a 1 correspond to the elements that I want to operate on. Okay? I can use it to index my matrix, AI, and I get the numbers in those boxes. All right? I can do find I if I'm interested in the indices of the elements that satisfy those conditions. The third element, the sixth element, 12th and 13th element of A satisfy those conditions using linear indexing, of course. So the third element would be 9. All right? So 9 is an odd number, and its logarithm is greater than 2. 11 likewise an odd number whose logarithm is greater than 2. So that's the sixth element. The 12th element is 15. Sorry, 12. 12th element is 15, and 13th element is 13. So the logical matrix I is a matrix that I can overlay on top of A. And I contains a true wherever my condition is satisfied. Okay? And what was I going to do with these? I was going to replace them with 0. So I would just say AI equals 0. So it will overlay this logical matrix on A and replace the corresponding elements with 0. All right? Now if you said find I equals 0, you would get the same result. Let me reset A to the magic matrix and repeat this, you get the same result. Okay? All right? So in one case, I was overlaying the logical matrix on top of A and only referring to the boxes in A that have a logical true in my index. And I was taking my logical matrix and finding the indices of elements that have a true in them, and then constructing a vector from them. So that says get me the elements that have a true in I, and those are the 3rd, 6th, 12th, and 13th elements, and then saying replace 3rd, 6th, 12th, and 13th with 0. So let me just say 99 so you see the difference. Okay? Any questions? All right. Now, here's a question that you guys should be able to answer. This piece of code is given, and you are asked to figure out which MATLAB function it is similar to. It's one of the functions that we discussed in the last 3 or 4 slides. Okay, I'll give you a minute to think about it. I should give out candy for correct answers. maybe bonus points. Do we have an answer? Alright, I'll give you a hint. It's gonna be either any or all. Okay, how many say any? How many say all? Alright, thank you for standing. Alright, so let's see what it does. It takes a matrix or a vector M and constructs a for loop that examines each element of M. Okay? So let's say this is M, and in each iteration of M, I am examining the element of M. If Mi is non-zero, meaning if it is true, this if condition will be executed. So this function returns RET, which is a variable. Initially, it has a false. And only when this if condition is true, I am placing the true value in the RET variable. Okay? If this Mi is never satisfied, then the value of RET remains false. So I go one by one. If I hit a non-zero entry like 5, then I'm returning true. So if any of the values in M is true, the result will be true. And that's the definition of any function. Alright? So XXX M is equal to any M. Alright? Okay, another exercise. Let's find the zero crossings in this vector. And the zero crossing is defined as the index where the numbers change sign. Okay? So this would be a zero crossing. So the number, you would return number 1 because the sign changes after the first element. This is not a zero crossing because the sign remains the same. They are both negative. They are both negative. This depends on whether you consider 0 to be positive or negative. Let's consider it to be positive. And this will be 1, 2, 3, 4. So you have 1. After the fourth element, the sign again changes. Positive to positive, the sign does not change. Positive to negative, the sign changes. So you get 5, 6. So write an expression that will give me these numbers, 1, 4, and 6. I'll give you a few minutes to think about it. And you can use the sign function, diff function, and find function. And I'll tell you what each of these do. If you apply the sign function to a variable, to a vector, it'll give you +1 wherever you have a positive number, and -1 wherever you have a negative number. And the way that zeros are considered may be tricky. I think zeros become 0. Let's test it. Sine 5 -5, 0, bless you. So all the positive numbers give you a 1, negative numbers give you a -1, zeros give you 0. But you should be able to take that 0 and make it a 1, because we are considering zeros as positive in our example. Alright. Diff function we've encountered before. It takes your vector and it looks at consecutive elements and gives you their difference. So it gives you the change in the values as you are going over your vector. And the find function we discussed in this lecture, it gives you the indices of a vector that has non-zero elements. and you would apply the functions given in the hint in the order that they appear. And you can use temporary variables too. I'll do the easy part and give you the answer for the for loop. So I would run over the vector for I equals 1 to number of elements in V. Since I'm going to be looking at pairs of elements, I actually need to I need to iterate over 1 less than the number of elements. So let's do 2 to the number of elements. Okay. And I will say if sine of Vi minus 1 is not equal to sine of Vi, then my output variable, let's call it y, n plus 1 equals I minus 1. Let me actually rewrite the indices, so it goes from 1, and I'll compare I and I plus 1. 1 to number of elements minus 1. If the sine of Vi is not equal to sine of Vi plus 1, then I'm going to add I to my matrix, to my output vector. Okay? And we want this without a for loop. You could actually do it without a diff, which might be easier. All right, let me get you started a little bit. So the first thing I would do is take the sine of V. And the sine of V will be 1, minus 1, minus 1, minus 1, 0, 0, minus 1. Okay? And then I would take the diff of that. So diff of the expression above is going to be equal to, can you guys help me write this? What's the first element? Minus 2. Next one. Next one. Minus 2, 0, 0, 1. Next one. It's done, right? There'll be one less element than your original vector because you are looking at pairs. Alright, so once you have this diff, before I go into this diff, I want to convert the zeros into plus ones. So let's take that step back. Let's say that in a temporary variable I equals sine of V. How do I replace all zeros with 1? I would have to construct a logical vector that contains a true for the elements I am trying to operate on. So I equal 0. I'm trying to operate on these two elements that contain a 0. And I will replace them with a 1. So that will make it so that my new I vector will have 1, minus 1, minus 1, minus 1. And I've operated on these zeros and replaced them with 1, 1, 1, minus 1. And then if I take diff of I, I'll get minus 2, 0, 0, plus 2, 0, minus 2. Okay? And then if I apply find to that, find the previous expression, it will give me 1, 4, and 6. Alright, let's do it in MATLAB. So V equals 5, minus 1, minus 2, minus 1, 0, 0, minus 2. And I take the sign of V. I get a 1 whenever it's positive, a minus 1 whenever it's negative, and 0 for 0. I want to consider zeros to be positive, so I will take the result of sign of V, and I will replace all of the 0 elements of I with a 1. Okay? So this says change the elements of I referred by this logical vector with 1, and the logical vector contains a true wherever the value is 0. Okay? So I get that. Next, I'm taking the diff of I, and it's going to take consecutive elements and give me their difference. And the definition of zero crossings was that the sign should change. So the diff will be non-zero whenever the sign changes. And I can find the entries after which the sign changes. That gives me the result. Alright? Make sense? Okay. Let's move on. There's a function, meshgrid, that helps you work with all combinations of elements. And when we did the Pythagorean example, we could have done it using a meshgrid function too, when we were considering all possible values for x, y, and z. Now what meshgrid does is you provide and a set of values for y. It generates a new matrix x and new matrix y, where it contains all combinations of x and y. So if you look at the first element of x and the first element of y, okay, the second element of x, the second element, all right, and the third element of x, you have 2, 1, and then a 2, 2, and 3, 1, 3, 2. Okay. So the first column that I displayed was x. The second column was y. So if you overlaid x and y on top of each other, you get these combinations. So this is a way to generate combinations of values of x and y. All right. It's also used in functions that take 2 or more arguments. Now we've already seen how to make two-dimensional plots. If you wanted to generate a three-dimensional plot, as an example, let's generate a three-dimensional plot of this function. You need to generate a grid of values on which you calculate the third axis. So when we were working in 2D, we were providing values for x. So to plot sine of x, we had to provide, let's say, 0.15. So we have to provide example values on which we want to calculate the sine of that. And then we would say plot 0, 0.1, 5, then sine of 0, 0.1, 5. And that will generate my plot in 2D. Okay? So for these values of x, I want to find the sine of x and make this plot. when we are working in 3D, now I have my z-axis, I have x and y axes. I have to provide a grid of x and y values as these dots. And for each of those, I need to find the value of the function z. And then it'll create a plot for those. Okay? So to be able to do that, I can use the mesh grid function first to generate the values for x and y. So if the values of x are 1, 2, 3, and the values of y are 1, 2, 3, 4, I need to call the mesh grid function to get a grid of those numbers. Alright, so let's do this in MATLAB, which will be easier to show. So we are asked to have x go from 0 with a step size of 0.1 all the way to 5. So that gives you 51 values in that range. And then y to be the same. So now I have my x and y. I'll generate a grid of these entries. Let me actually start with a simpler example that'll fit on my screen. And then let me call that capital X and capital Y equals mesh grid X, Y. So that will create a 4x4 matrix X and a 4x4 matrix Y. If you overlay them on top of each other, it's a grid of X and Y coordinates where they start from X equals 0, Y equals 0, and go all the way to X equals 3, Y equals 3. Okay? And I can take these X and Y values and make my three-dimensional plot. Making three-dimensional plots is very similar to making two-dimensional plots, but now instead of 2 variables, you need 3 variables. So I'm going to provide x, y, and the function that I'm trying to plot, which is going to be x multiplied by sine of x plus 2 times y. And I should get my figure soon. There you go. Alright, now the figure is not very pleasing because the range of x values I used was only 4 values, and similarly for the y values. I need to increase this range and make it more refined. I have to use a higher resolution with a step size of 0.1. And I will generate the grid again, but now I'm not going to display them because it's going to be 51 times 51 elements, actually more than that. And I can plot it. It will generate this nice graph. Okay. And then let's put labels on it. X label, X, Y label, Y, Z label. If you rotate it, you see that for each value of x, it's going through the values of y and plotting a two-dimensional plot, a two-dimensional line that corresponds to the values of z. Now, instead of plotting lines, you can plot a surface using the surf function. The arguments are the same. So instead of plot 3, you would call surf. So it'll generate the surface. Okay? Any questions? Alright, so if I rotate this and look from the top, I am looking at x and y axes, and I am my resolution is x starting from 0, increments at 0.1, going all the way to 5. So MATLAB will only calculate values of z for those input values. Okay. Any questions? I should have more than this in the slide. Looks like I don't. All right. I've lost some content in my slides. Let me just create an empty slide for you. So in MATLAB, there are some aggregator functions, and this is the topic of basic statistics. Aggregator functions. So they take a matrix or a vector, and they return you a single number or a vector of numbers. So they would reduce the vector, they would reduce the matrix into a single vector, and they would reduce the vector into a single number. We've already seen examples of these, such as sum, which gives you this sum of all numbers in the vector. Now these aggregator functions work along a dimension. So what do I mean by that? When you have a matrix, M, if you say sum of M, it's not going to give you the sum of all elements in the matrix. What it will give you is a new vector with the sum of each column of your input matrix. Alright? So let's try that. Let's have M to be a magic matrix. And let's take the sum of that. I get a row vector that contains the sum of each column. What if I wanted to take the sum of each row? What would I have to do? Well, I can take the transpose, but in this case, since they are all end up to be the same number, let me change it a little bit. 3 by 3. So if I take sum of M, I get the sum along each column. If I take the transpose of M, I get the sum along each row. But to actually see it better, let's 5, 10, 15, and then you get 24. You can take the transpose again to have a column vector. Okay? So sum of M gives you a row vector with the summation of each column, and you can take the transpose of M and the transpose of the result to get the sum of each row. Or you can look at the documentation for the sum function. And you see that the sum function takes an additional argument dim, which stands for dimension. And let's read what it says. Here it is. So sum A, comma dim, sums along the dimension of A specified by scalar dim. The dim input is an integer value from 1 to n, where n is the number of dimensions in A. So if dim is 1, we would calculate the sum along each column. If dim is 2, we would sum the rows. If you are working with three-dimensional matrices, you would, for instance, provide 3 to sum along the third dimension. So instead of doing this transpose, I could say M, comma 2. That'll give me the sum along each row. All right? This is an important concept when you are using aggregator functions and working with matrices, and you need the summation along a row or a column. All right. Now, there are some other functions that work in a similar manner, such as prod, that gives you the product of each row or each column. Okay. The min function works in a different way, in the sense that it has, by default, an additional argument that you need to provide before providing the dimensionality. So the way that the min and max functions were initially designed, they were designed for two scalars. Okay? So you are providing them with A and B, and it would return you A or B depending on which one is smaller or which one is larger. Okay, so min 3, 5, 3, max 3, 5, 3, 5. Now, when one of these input arguments is a matrix, then MATLAB will do element-wise min or element-wise max. So min of 3, 5, 7, 2, comma 4 will give me what? It's going to give me a matrix. Can you guys tell me the elements? What's the first one? So you're basically applying min of 3 and 4, you'll get a 3. Min of 5 and 4, you'll get a 4. Min of 7 and 4, you'll get a 4. Min of 2 and 4, you'll get a 2. Right, so it's taking the matrix and the scalar and applying the min function to each matrix element. If your matrices have the same size on both sides, instead of having instead of having a scalar, let's say for 1, then the result will be min of 3 and 4, which will give you a 3, min of 5 and 1, which will give you 1. So your matrices should either be, they should both have the same size, or one of them should be a scalar. Similar to the rule that you had for adding matrices or multiplying matrices element-wise, okay? All right. So if I do min of a matrix, just like sum, it works with a single matrix, and it'll give me the minimum along each column. All right? So the minimum along the first column is 5, the minimum value along the second column is 1, and so on. Now to find the minimum along the row, I need to provide another argument dimension, but I cannot do it in the same way as I was using sum function. So it's sort of tricky, so let's just use the documentation to see what it has to say. And it tells you to use min AB. You would provide either two matrices, or you would provide A, comma, empty matrix, and then a dimensionality. All right? So if I were to say min M, comma 2, that will look at the matrix M and the number 2, and it will do element-wise minimum. To ask for MATLAB's min function to provide minimum values along each row, I would have to provide an empty matrix here. Okay, that'll give me 5, 7, 1. All right, and there's a homework question on this, where you take the minimum and maximum along each row and along each column. So max works exactly the same way, and the product function works just like the sum in terms of whether you are taking rows or columns. Okay. Now the diff function again has a special second variable. And if you start typing the parentheses, you'll get some example uses. You can either provide a matrix, you can provide a second argument n, which specifies how many times you apply the diff function. So M was this matrix. If you apply diff of M, you are looking at, you are going column wise, okay? And you are taking the differences in each column. So you go along the first column, 5 to 10, you have a difference of 5. 10 to 8, you have a difference of -2. Second column, 10 to 7, you have a difference of -3. 7 to 1, you have -6. Okay? Now you can apply diff multiple times, which is the second argument, that will take the diff of the diff. So 5 going to -2, you have -7. -3 going to -6, you have -3, and so on. If you want to diff along the columns, you would have to specify the column which is 2, sorry, the row which is 2 as the last argument, as the third argument. Okay, so you are switching the dimensionality along which the function is applied. All right, and you can increase the number of times that diff is being applied. Any questions? All right. When you apply min and max, they give you an additional output argument. So x will be the minimum value, and I will be the index of that minimum value. So min of m, where m was this matrix, gives you 5, 1, 7. You get a minimum along each column. If you capture both the minimum and the indices of those entries, then you'll get 5, 1, 7. And this index refers to the locations of the entries that were minimum. So for the first column, the minimum was in the first entry. In the second column, the minimum value was in the third entry. And in the last column, the minimum was in the third row. Okay? If M is a matrix, you have a slightly different behavior. Let's see what it gives us. Min 5, 7, 4, 9. xi equals. So I had this matrix, okay? And then when I took the minimum, it gives me the minimum along each column. So the minimum in the first column is 4, in the second column is 7. And then I is the same. Well, I already described this. So you guys already know that it should be 2, 2, and 1. I thought we would have to deal with something else, but no. Okay, so tell me the result of the first one. What will x be? I already showed you in the MATLAB. So what's the value of x after this first operation? Who says 4? Who says 5? Who say 4 and 7? Right, well, the answer is going to be 4, okay? If you have a vector, the min function will look at the entire vector. Whether it's a row vector or column vector, doesn't matter. It will give you a single answer. It will give you a single number. And then the value I will be the index of that. So after this operation, x will be 4 and I will be 3. And the second problem we already solved. You have to look at the matrix 5, 7, 4, 9. If you take the minimum, x will be 4 and 7. Okay. And I will be the second element 2, first element 1. Make sense? All right. That's all for today. And exercise is on the web. Let's see what it is. You guys are anxious to go home. If you've already looked at the exercise, I guess, and you feel comfortable with it, you can go, but let me quickly. So the myAll function, you would basically try to write a for loop that will give you, that will tell you whether all elements. And I already showed you a for loop that contains the any function. And in the second exercise, you are asked to write an expression, a mathematical expression that will find the sum. You can use the